Richard James Mathematics Resources are ready to present Grade 4 Practice Paper 2, and we will begin with Part A. The first three videos, A, B, and C, will contain the solution of 12 mathematics problems. Video D will not only have the remaining multiple choice problems, but also the essay type problems to be answered. Let us begin. On this occasion, we are required to add 479 and 78. Let us add the numbers by writing down the first number, which is 479. Write down the place value of the digits, beginning with the smallest place value. We will write the place values down also. Place values are good to be included. They act as a reminder, a constant reminder, as to the place value of the digits in a number, and that is going to be very useful at the grade 4 level. So let us write down the place values, beginning with the 1 to the right, and that's your ones digit, then your tens digit, followed by your hundreds digit. Next, we will write down 78, but we cannot just throw in 78 from a distance. We will write 78 by first placing the ones digit under the ones digit. So in 78, what is the ones digit, Jerry?
8.
Okay, so we put that down first. And where do we put the 7?
Under the 10.
Right, so the 7 will be included in the tens column. Place the tens digit under the tens digit. That means we are placing the 7, which is the tens digit, in the tens column. So the next thing that we will do, if we are adding, we will write the addition sign, and we will also draw our line. And I realize that these days students are very shorthand. What they will do is use the line that is in the book as the line that should be drawn, instead of actually drawing an additional line showing that we need to add the numbers and also including the addition sign. So students will not want to put another line for themselves, but they will assume that the line that is in their notebook is sufficient, and that is not correct. So we will deliberately put in a line or draw another line in addition to the ones that we have in our exercise books. Begin by adding the ones digit. When we are adding numbers, we add the digits to the extreme right first. So those digits that are to the right are the ones that we will add first. Therefore, Jerry, what digits do we add first?
8 and 9.
Right, so we'll add those, 8 and 9. What's 8 plus 9, Jerry?
8 and 9 is 17.
Okay, so 17 is correct. So 9 plus 8 is equal to 17. What do we do? Do we put the entire 17 in the ones column?
No.
Okay. So place the 7 in the ones column and carry the 1 to the tens column. And it is for us to understand that when we have a sum in the ones column of 17, that the 7 will go exactly in the ones column. But the 1 is a digit of greater significance, and its place value, not the value of the digit, but its place value is 10 times the place value of the one that we have here. Therefore, when we place the 7 in the ones column, because this one, its place value is 10 times the place value of this 7, it will go to the other column. Because if we are at a particular column, each column to the left of your present column has a place value that is 10 times your present place value. Therefore, if you are in the ones column, the digit to the left will have a place value 10 times the ones digit. And if you are in the tens column, then the digit to your left, which is the hundreds digit, will be 10 times your present place value. Therefore, when we get a sum of 17, the 7 will be 7 ones, and the 1 will be what? Tens. So the 1 will go in the tens column. That is why we say place 7 in the ones column and carry 1 to the tens column. Add the tens digit. So we will add the tens digit, and no doubt the one that we carried will be a part of it. So when we add these numbers, Jerry, what will be the result?
15.
Right. I like to ask Jerry right off the top of my head so that Jerry will give the answer. If it is given to me very quickly, then I know that he is sharp and on top of his game. But sometimes Jerry will be sitting down there and he does not imagine that I will ask a question. So I take the opportunity to surprise him sometimes. But I did not catch him with 1 foot on the ground on this occasion. So Jerry supplied the answer 15. So what do we say now? Place 5 in the tens column and carry 1 to the hundreds column. Add the hundreds digit. What will we get when we add the hundreds digit, Jerry?
4 plus 1 equals 5.
Okay, as long as you do not forget that we have the 1 also to be included. We may include that 1, so we get 4 plus 1, and that is equal to 5. Place 5 in the hundreds column. We are adding the hundreds digit, therefore the result will go into the hundreds. Right. So there we have our correct answer, and that is represented by what option?
Option A.
Right, so the correct answer is option A. What we have here is 16 divided by 4. We are dividing. If we are dividing, then we are required to have a particular format when we are dividing. So we will make sure to include that format. This is a division problem. Let us set up our division format and use short division. So this is a division problem, so use our division format. What we have here is saying 16 divided by 4. And what we have here is saying 16 divided by 4. We will first attempt to divide 4 into 1, because when we are dividing, we begin at the leftmost digit. So we will say 4 into 1. We can't. So we say 4 into 16. So when we use one digit and one digit is not enough, or it is less than the number that we are dividing by, which is the divisor, when our first digit is less than the divisor, what do? We include the other digit. So we say first 4 into 1. I can't. Not that we can't, but it will not go a whole number of times. Right, so 4 will not go into 1 a whole number of times. So we move on to the 6 and we say 4 into 16. Now, what we should really do, or what we should really consider, is that if we say 4 into 1, we should really consider that a 0 needs to be here. The 0 is not there because when we are through, a leading 0 will not contribute to the value of the number. So it does not change the value of what else is presented. Therefore, we may discard the 0. So we can forget about it, or we can just not put it. But we are sure that if we say 4 into 1, we will not get that going a whole number of times. So actually, we should have no time here, and 0 could have been placed there. But in the final analysis, it will not contribute to the value of the number, so we may leave it out. So 4 into 16 goes how many times, Jerry?
4 times.
Jerry said 4 times. So 4, 4, 16. So 4 into 16 goes 4 times. The correct answer is therefore
Option A.
Option A. So option A is our correct answer. And if we are dividing, it is good if we understand that division is the opposite of multiplication. And division is something that is closely related to our multiplication tables. So we may take an approach that makes use of the fact that division is the opposite of multiplication. Because of that, we may consult our multiplication table. So we can also consider that our division problem is a multiplication problem in the reverse. So we have 16 divided by 4. This one is the dividend, this one is the divisor, and this one is the quotient. If we multiply the divisor by the quotient, the result will be the dividend. What number do we multiply by 4 and the result is 16? So if we are dividing, and this is required to be the answer, we are dividing by 4. If we are dividing by 4, it means that when we multiply 4 by whatever we get here, the result should be 16. Division is the reverse of multiplication. So if we say 16 divided by 4, whatever we get here, if we multiply this number by 4, the result is 16. So we are actually saying, what number do we multiply by 4 and the result is 16? You should have the answer at the tip of your fingers, like Jerry did, and he supplied it just a few seconds ago. If you are sharp on your multiplication table, then you would have no difficulty doing that. So you should have the answer at the tip of your fingers if you are sharp on your multiplication table. What number do we multiply by 4 and the result is 16?
4.
Alright, so Jerry is sharp. He has his multiplication tables right at the tip of his fingers. But we are putting them there and they will disappear, so make sure that you catch it. Well, Jerry does not need to catch it because he knows his multiplication table. So 4 4s, 16. So we say 4 fours, 16. So the number that we multiply by 4 and the result is 16, that number is 4. And that means that if we divide 16 by 4, the result is 4. It is easy to add fractions if their denominators are the same. If their denominators are the same. So we are about to add fractions. Are their denominators the same, Jerry?
Yes.
What are the denominators equal to?
12.
Right, so we have the denominators being equal. Each one is equal to 12. So we have our fraction and we have the parts of the fractions being listed right there or identified right there. So the fraction contains a fraction bar that divides the numerator from the denominator. Divides or separates the numerator from the denominator. And the one number that is the lower region, that one is the denominator. And the one in the upper region, that one is the
Numerator.
right. If we are adding fractions and the denominators are the same, then we may just go straight ahead and add those numbers. Is that right, Jerry?
Yes.
Okay, so the addition should be straightforward. When the denominators are the same, the resulting fraction will have the same denominator as the fractions added. So when we are adding, we are sure because we know the answer for the denominator or we know the denominator of the answer already. Why? Because the denominator of the answer will be the same as the denominators that we have here because the fractions have the same denominator. And later on, we will take a look and see why that is so. So the denominator will go first. First, because we know that when we add fractions with the same denominator, the fraction that results will have the same denominator. The resulting numerator will be the sum of the numerators. What do we have for the numerators, Jerry?
4 and 5.
Right. And when we add them, the result will be
9.
So we add those numerators, 4 plus 5, and the result, as Jerry outlined to us, is 9. The correct answer is option
C.
right. So when we add numbers or fractions with the same denominator, the answer will have the same denominator and the resulting numerator will be the sum of the numerators of the fraction. In a short while, we will take a look at the reason for using the same denominator when the fractions that we are adding or subtracting have the same denominator. And just add the numerators. We will also see the reason for arriving at a common denominator when the denominators of the fractions are different. So we will see the reason for using the same denominator when the denominators of the fractions that we are added are the same. And we will see why we need to arrive at a common denominator when the denominators are different. So, right here, we are taking a look at why we can add fractions with the same denominator. But if the denominators are different, we need a common denominator. What do we have right there? How many cupcakes do we have, Jerry?
3.
We have 3 muffins. Let us take another 4 muffins. We have 4 muffins. So how many do we have, Jerry?
7.
7 what?
Muffins.
Right, so we have 7 muffins. How many do we have? Count them. Well, we can count them. We can say 7 muffins in all. Why may we say that? We may say 7 muffins in all. Why may we say that? Because they are all the
Same.
They are all the same. We therefore do not have to say 3 muffins and 4 muffins. But we may say what?
7 muffins.
Right, so we may say 7 muffins all together. Why can we say that? Because they are all muffins. So if we add 3 muffins to 4 muffins, we have 7 muffins altogether. So what do we have there on this occasion, Jerry? We have 3 muffins again. So what if we take 3 muffins and add to them 4 lollipops? 4 lollipops. Can we say that we have 7 of one thing?
No.
We cannot say that. There are still 7 of them in all. But how do we say that?
There are 3 muffins and 4 lollipops.
Right. Jerry is saying that we have to say we have 3 muffins and 4 lollipops. If we say 7 lollipops and muffins, then no one will be able to say how many of each we have. Say, for example, Jerry, if I say that I have 20 lollipops and muffins, we have 20 in all. Are you able to say how many of each do we have?
No.
No. So if we say 7 lollipops and muffins, then no one will be able to say how many of each we have. Because they are not the same, we cannot assign a single number to them. To be clear, we will still have to say 3 muffins and 4 lollipops. So we cannot just give a single number or a single collective name for them. We still have to say that we have what? 3 muffins and 4 lollipops, because they are not all the same. Because if we say there are 7 of them, it will not be clear how many of each we have. And the information will not be sufficient, or it will be deliberately misleading. There we have 2 shapes. Each of them is divided into 8 equal parts. Each of those equal parts is called an eighth. So we have 2 diagrams right there. 2 shapes. 2 identical shapes, as a matter of fact. So what do we say? How many parts have we taken out of the first, Jerry?
3.
And that is representing 3 eighths. How many eighths?
3 eighths.
Right, or 3 parts out of 8 equal parts. We have taken out 3 parts out of 8, which is called 3 eighths, and written as 3 over 8. Let us take out another 4 parts out of 8, called
4 eighths.
4 eighths, and write 4 out of 8. But this time we are not taking the eighths from the first one as we did. We are taking those eighths from the other one. So what do we have? How many eighths are we taking now? 4 eighths. 4 parts out of 8, or 4 eighths. Are we able to say that we have a total of how many, Jerry?
7.
7 what?
7 eighths.
So we have 7 eighths. Can we say that?
Yes.
Why can we say that? Because they are all eights. So we can say 7 eighths. Irrespective of the fact that we got 3 from this and 4 from this one, altogether we have 7 eighths. In all, we have taken out 7 eighths, as we see there. It does not matter whether or not they are from different objects. They are mathematically identical because each comes from an object that is divided into 8 equal parts. Each of them is an eighth. We may call them by one number, 7 eighths. Right. So they are identical because they are all eighths. So we can say that we have 7 eighths. Again, we have two shapes. However, one is divided into 8 equal parts, which is, they are divided into eighths, and the others into 6
Equal parts.
and those 6 equal parts are called sixths. Right. So we have taken out how many eighths, Jerry?
3.
3 eighths. And we have taken out 3 parts out of 8, which is called 3 eighths, and written 3 over 8. Let us take out another 4 parts out of 6 this time around. So on this occasion, we will take our 4 parts out of 6, called 4 sixths, and written 4 over 6. So we have 4 parts, and those 4 parts are taken out of an object that is divided into how many equal parts?
6.
No. We have 3 eighths and 4 sixths. Can we just say 7 eighths and 6, Jerry?
No.
We cannot say that because they are not identical. In all, we have taken out how many parts?
6.
We are taking out how many parts?
7 parts.
We have taken out 7 parts, but they are not identical. You can tell me why, Jerry, is it that these parts are not identical? Why they are not identical?
Because one has 7 parts and one have 8 parts and one has 6.
Right, so one was divided into 8 equal parts and the other was divided into 6 equal parts. So they are not identical. In all, we have taken out 7 parts, but they are not identical. Some are sixths and some are eighths. We therefore cannot refer to them by using one number, because no one would be able to tell how many of each unless he or she sees them. We therefore have to say 3 eighths and 4 sixths. Right, so we cannot assign to them one name saying that we have 7 eighths and 6, because we will not be able to tell the number of each. Because they are different, we have to single them out and call them differently. That is why when we are adding fractions, we may go straight ahead and add them if they have the same denominator. That means the whole is divided into the same number of equal parts. Then we may add them as we did on the previous slide, where we add 3 eighths to 4 eighths and we ended up with 7 eighths. That is acceptable because each of them was divided into 8 equal parts. So all of the parts that were added are eighths. There's no difficulty. But on this occasion, one is divided into eighths and the other into sixths. So we cannot go ahead and enlist them by making use of one name or one number. This is why when we are adding fractions with the same denominator, we may assign the same denominator to the answer. But when we are adding fractions with different denominator, we have to find a common denominator. As we go through these videos, I will explain why a common denominator is appropriate. Why a common denominator is appropriate. In this problem, the numbers are already presented in the way that we may add them. Begin by adding the digits to the extreme right, and at the extreme right is where we find the digits with the smallest place value. So we will begin with the smallest place value, and that will be at the rightmost digit, which is right there. So we have 4 plus 5 plus 3, and that is equal to what, Jerry?
12.
Next time when I'm asking you, I will not have the answer on the screen, so be prepared. Now that 12 that we have there has a ones digit that will remain in the present column, and the 1 will be a digit of greater significance. It will be carried to the other column. So write down 2 and carry 1 to the next column. When we add those digits, what will we get, Jerry?
16.
Jerry said 16, but I have some doubt.
15.
Go again.
15.
Right, so they will be 15. When we add them, the result will be 15. So 1 plus 6 plus 6 plus 2, and that is equal to 15. So what do we do?
Carry the 5 down and carry the 1. Put the 5 down and carry the 1.
So we'll put the 5 down, and the 1 will go to the column of greater significance, which is the column to the left. So the present digit, which is this one, will go in its present position. But the 1 is a digit of greater significance, and it is carried to the column of greater significance. Vertically align the points with the others. So we are adding decimal fractions. The point has to be included. We have to give serious consideration to the point, and we have to make sure that it is present. So we will ask again when we go to the... So let us move merrily along to the ones column. When we move merrily to the ones column, when we add them, what will be the result?
15.
So the result will be 15 again. So what do we do?
Put down the 5 and carry the 1.
Right, so the 5 will remain in its rightful place, and the 1, being a digit of greater significance, will be carried to the column of greater significance. And what do we do with the other one? When we add those digits, what do we get?
12.
12. So we will get 12. Add those digits, and the result is 12. The 2 will remain in its rightful place,
Carry the 1.
and the 1 will be carried to the column of greater significance. And finally, when we add those digits, the digits of greatest significance, what do we get?
3.
Right, so finally add 1 and 2 in the last column, which will be the column of greatest significance, and the result is 3. What option does that represent?
Option A.
And that is represented by option A. But we have our reminder that we have to include what?
The dollar sign, because we're dealing with money.
Right, so we are dealing with money, so we need to include the dollar sign. We cannot leave that out. It is very important and has to be included. Else when we add the numbers, no one will be able to tell that we are adding dollars. As a matter of fact, it will just be a pure number. The correct answer is option A. Now, we have some numbers that we are required to add. What do we need to give serious consideration to when we are adding these numbers? What do we think about? What do we consider? What do we do? We may write the first number down first, right? And if there is anything that we need to do, then we will make sure that it is done properly after. We need to write down the other number. What do we do? First thing that we give consideration to is what?
Decimal point.
Right, so Jerry is saying that we should give serious consideration to the decimal point. So in writing down the first number, we just write it down. But when writing the other number, we have to make sure that the decimal points are vertically aligned. So when writing the other numbers, make sure that the points are vertically aligned. So your point will be placed vertically below the point of the first number. The other digits should be appropriately placed on either side of the point. So we have 265.73. 265 will be placed on the left-hand side of the point with the digits also vertically aligned. And no doubt, the 73 will be placed on the right side of the decimal point with the digits vertically aligned with those that we have there before. So we may also give consideration to place value, but that is too technical. It's not that it is too technical to be done in grade 4 because we should be able to do it. But for a problem that we need to solve like this one, paying attention to the decimal point will suffice. So the numbers are distributed properly on either side of the decimal point. And we do the same with 15.6. The point will go first, vertically aligned with the others. And what do we do with the rest of the digits? We make sure that they are appropriately vertically aligned on either side of the decimal point. Although they are not necessary, when adding numbers, we will include the place values as a reminder. So it is not necessary on this occasion, but we have the place values, hundreds, tens, ones, tenths, hundredths, thousandths. So all of those place values are included. We do not have to have them in order to add the numbers, but including them is very useful at this stage in which students are required to know and understand place value. So after the decimal point on the right side, we have the tenths, then we have the hundredths, then we have the thousandths. As we have seen in previous problems, placeholding zeros are not necessary when adding numbers, but we will include them here nonetheless. So we will fill the empty spaces with placeholding zeros. Although if we add without the placeholding zeros, we know that where there is a blank space, that there is no number there. And if no number is there, then the value that is present there is 0. So include placeholding zeros. They do not affect the value of the numbers. Begin by adding the digits to the extreme right. They have the smallest place value. So go to the extreme right and we add those. What's the answer, Jerry?
1.
That's very easy. We like to add numbers that contain a letter 0 inside there because we know the zeros don't amount to anything and the result is easily obtained. So begin by adding the digits to the extreme right. They have the smallest place value. Only a single 1 along with those zeros. Therefore, 1 plus 0 will be 1. And although we have a 0 there, what is the answer in this particular case, Jerry?
11.
11. So 11 contains 2 digits. This digit will be placed in its rightful place, right? In the 100th, right in the 100th place value. So we will place that there. And the other digit is of greater significance and will be carried to the column of greater significance. And when we add those, Jerry, what do we get?
14.
Right, so it is 14. 7 plus 1 plus 6, and we get 14. And we can see that we have a 1, put it with this 6, we get 7. And because there's a 7 here, we say 2 sevens, 14. So by doing that, the 4 will be placed in the same column. Right, so the 4 will be placed in the same column. And the 1, which is the more significant digit, will be carried to the column of greater significance. But do we just jump over and start to add again?
No, we put it in the decimal point.
Right, so we need to include the decimal point. So let us include the decimal point. We know that the correct option is D. Only it ends with 411. We may continue to confirm. So notice that when we add these, we have 411. The only option that ends with 411 is option D. This one is 311. This one is 414. This one is 810. So the one that ends with 411 is option D. We have discovered the correct answer already. So we do not need to do anything else. However, because of the nature of these videos, which is to instruct, inform, and to overall educate, we will continue to add the digits. But we cannot do that, as Jerry stated before, without including the decimal point. So let us cause the decimal point to be vertically aligned with the decimal points that we have there already. Then what do?
5 plus 5 and 5 and 7 plus 1.
That will give us what?
18.
18, right? Because we can see these 5s adding to give 10, and then we have 8 right there. So that's 18. Add the digits in the next column. We have done that already. So 18. Finally, well, not quite. When we add these digits, what do we get? Add the digits in the next column. What will be the result?
17.
Very quickly, because 9 plus 1 will give us 10, and this is 7, so that's 17. We can associate numbers that are easily added. When we have quite a few digits to add, then we can make an association that will cause the numbers to be easily added. For example, when we add 9 to 1, the result is 10, and then we may just include this 7 right there, and we arrive at 17. Then we will write down 7 and carry 1 to the next column. And finally, we will add those Jerry is saying 2 plus 0 plus 1, and the result is 3. So let us put the 3 right there. Do we have the other digits being equal?
Yes.
Yes. So even though we discovered already that by the ending 411 that option D is correct, we still went ahead and do the rest of the calculation, and we see that they are all correct. Now we need to multiply, and not only multiply, but we are multiplying by 45, which contains 2 digits. What do we do on this occasion? We need to perform the operation as given, and it requires that we multiply the numbers. When multiplying numbers like that, Jerry, where do we begin?
At the ones column.
Right, because on this occasion, the ones column contains the digits of least significance, or the digits that represent the smallest place value. So let's go. When multiplying numbers, we begin with the numbers at the right. They are the ones with the smallest place value. So begin right there. So notice that we are beginning with what? The ones digit of the multiplier and the ones digit of the multiplicand. So 5 6s 30. And as usual, especially on this occasion, we'll have to pay special attention to the way that we proceed, because the numbers are going to be very much larger than the ones that we had before. So for these numbers, we will have more to carry. And since we are multiplying, we have to pay special attention to what we do after we carry the digits. So the first one that we have there is 5 6s 30. And as usual, you imagine that we will write down 0 and carry 3 to the next column, because the 0 will be the present digit, will go right there, and the 3 will be the digit of greater significance. So it will be carried to the column of greater significance. Now what do? We say 5 5s 25. And what do we do after that?
Add the 3.
We add the 3. So 5 5s 25, and then to the 25 we add the 3, and we get 28. So 28 is what will belong here. So what do?
Put down the 8 and carry the 2.
Put the 8 down and carry 2 to the column of greater significance. So let us do that. And what do we get? What do we do next? We say what? 5 2s.
10.
And write down 10?
No, you add the 2.
We need to add the 2 that was carried. So 2 will be added to the 10, and 2 plus 10 will be 12. So we have 5 2s 10, then we add the 2 that was carried, and we get 12. But because there is no other column, then we may just write the 12 down. So write down 2 and carry 1 to the next column. However, what do we need to do? Do we multiply again?
No.
We do not multiply. All we need to do is just include the 1 that is in the thousands column just as it is. There is no other number to be multiplied. The one that was carried to the thousands column will be the thousands digit. So we may write that down. And some individuals will not give too much consideration to that. But because there is no other number to multiply after this 2, we say 5 2s, 10. Then we add the 2 to it and we get 12. What do? We just write the 12 down. But of course, it is good if we can consider that the one that was carried to the column of greater significance. So it was carried to the thousands column. So it will be the thousands digit. And with nothing to multiply, we will just write down that single thousandth digit as it is. So we have multiplied 256 by 5. What do we do next? We also need to multiply the 256 by 4. But how do we do that? We will then move to the tens digit of the multiplier. So we multiplied the 256 by making use of the ones digit of the multiplier. This is the tens digit of the multiplier. So what do? Move to the tens digit of the multiplier. We are multiplying by the tens digit. So if we are multiplying by the tens digit, do we put a number right here?
Yes. No.
So we do not put a number right here because we are multiplying by the tens digit. So there will be no ones. So we are multiplying by the tens digit. There will be no ones in the answer. We may include a placeholder 0 or leave the space blank. Our first value will go in the tens column. So because we are multiplying by the tens digit, our first value will go in what column?
Tens.
It will go in the tens column. So we may leave the ones column blank, or we may put a placeholder 0 there. So 4 6s.
24.
Right. Write down 4 and carry 2. 4 6s 24. Write down 4 and carry 2. So the 4 that we write down, which column will that go in?
The tens column.
It has to go in the tens column because we are multiplying by tens. We will not get any ones in our answer. Then we say 4 5s.
20.
20.
Plus 2 equals 22.
Right, so the 2 that was carried, we will add it a little bit later. So we say 4 5s, 20 plus 2, and that gives us 22. So we multiply the 4 by the 5, the result is 20. Then we add 2 to the 20, and we get 22. And what do we do with that 22?
Put down the 2 and carry the other 2.
Write down 2, the present 2, and carry 2 to the column of greater significance. 4 2s.
8.
Do we just write down the 8?
No, you add the 2.
Okay, so we cannot just write down the 8, but we need to add 2 to it. So add 2 to the 8 and we get
10.
10. So 4 times 2 is equal to 8. Then the 8 plus 2 that we have right there carried over is equal to 10. So write down 0 and carry 1. But this one will go into the thousands column. Right. The 1 was carried to the thousands column. We are not multiplying it, but our multiplier is the tens digit. It will therefore be placed in the tens of thousands column. So the 1 that was carried will be placed where?
The tens
of thousands column. We will now add the two products. Remember that when we multiply by the 10th digit, there is no 1 digit in the answer. So we will add those first. Apart from that 0, there's nothing to add in the ones column. The result of the ones column will be
0.
So 0 goes there. Then when we add those, a plus 4 equals
12.
So we will put the 2 in the present place value column and carry the 1 to the column of greater significance. And then when we add those numbers, what will we get?
5.
Right, so do we have any carry on this occasion?
No.
So write 5 down and there is nothing to carry. What about the others?
Nothing to carry.
Nothing to carry, just 1 plus 0, and that is equal to 1. And what do we do there?
Carry the 1. But there's nothing to add.
Okay, so there's nothing else to add to that 1, so the 1 will be placed in our tens of thousands column. And that's all there is to it. The correct answer is option
D.
Okay. This one does not have just symbols alone, but it is also worded. It says, divide 5,025 by 5. This one, we need to pay special attention to it, because in this one, we will clear up some misconceptions. We are required to divide. We will set our problem in division format. So let us set the problem in division format. We have done that in one step. What do we do next? We say 5 into
5. 1 time.
Okay. We say 5 into 5 goes 1 time. So we will first say 5 into 5 equals 1. Any number divided by itself is equal to
1.
What do we say next? Then 5 into 0. Can we do that? Can we divide 5 into 0? We can't. So we put a 0. Put that 0. What do we say next?
5 into 2.
Why do we just say 5 into 2? No. It is for us to understand that we are not forgetting the 0. But because if we say 5 into 0, 2, the 0 that is leading here does not have any significance, or it does not contribute to the value of the number. Because it does not contribute to the value of the number, then we proceed as if we do not include it. But we have to give consideration that the principle that we are applying is that we are considering the 0. Why do we say that we are considering the 0? Because we say 5 into 0, we can't. And we have to carry this digit until 5 can divide into the number, or the entire set of digits are exhausted. So we say 5 into 0, we can't. Then we say 5 into this, which turns out to be the same thing as 2, because this 0 does not contribute to the value of the number. And again, we say that we can't. And what do we do right there, Jerry?
Put a 0.
We'll put a 0 right there. We then say 5 into 2. But the 0 is not forgotten. It is a part of the new number. But because it is to the left of the non-zero digit, it does not affect the value of 2. Again, we can't, so we place a 0 over the 2. So what do we say now, Jerry, after we can't? We say into?
25.
Right, we say 5 into 25. But remember that we said 5 into 0 we can't. 5 into 2 we can't. Or 5 into 0 2 we can't. So we also need to keep this digit with us. We need to keep this digit. So what do we say? 5 into
0, 25.
right. So we are really saying 5 into 0, 25. But the 0 does not affect the value of the number. So what we are doing is with the consideration that the value of the number is just 25. But we have to have the principle in our mind that we have not thrown away the 0. But it is a part of the number, but it does not contribute to the value of the number. So we say 5 into 25, and what will we get?
5 times.
5 times. So we proceed to say 5 into 25 because we have not forgotten any of the previous digits. However, the leading 0 does not affect the value of 25, but it is a part of the number. 5 into 25 goes 5 times. The correct answer is option
C.
right. The correct answer is option C. Which number is the divisor in this expression that we have right here? What number is the divisor? The divisor is the number that we are dividing by. So which number is the divisor in that case, Jerry? What number are we dividing by?
574.
We are dividing by 7. So the number that we are dividing into is 574. But the number that we are dividing by is 7. So the expression that we have there may also be written in another way. So we have another way of writing it. 574 divided by
7.
and the result is 82. The number that we are dividing into is called the dividend. So the number that we are dividing into is the dividend. And we are identifying the dividend in each case. The number that we are dividing by is called the divisor, the one that we are dividing by. So we identify the divisor in each case. And the result is called the what? It begins with a Q. Quotient. Right, so the result is called the quotient. So the answer or result of dividing the dividend by the divisor is called the quotient. So there we have our quotient being identified, which is the result that we get when we divide the dividend by the divisor. The correct answer is therefore option
C. Option B.
in the number. Which number is the divisor in that one? So the correct answer is option B. The diagrams show fractions of the same size objects. Use the diagram to answer question 9, which is what? What is a half plus a quarter? No. Plus 3/4. What is a half plus 3/4? The diagram shows fractions of the same size object. Use the diagram to answer question 9. What is 1/2 plus 3/4? A half plus 3/4. So there we have our half is the first one, and then we have 3/4, the other one. Fractions may be added if they have the same denominator. If they do not, then we bring them to the same denominator. How do we do that? So there are two fractions to be added, and they have different denominators. How do we bring them to the same denominator? If the denominators are the same, we just proceed and add the fractions. But on this occasion, the denominators are different. The same denominator means that the whole is divided into the same number of equal parts. But as we have them, one is divided into fourths, 4 equal parts, and the other into halves, 2 equal parts. They need to be divided into the same number of equal parts without affecting the dividing lines that are there, creating divisions that halves and quarters can fit into. So what we will do here, we will create divisions that the halves and the quarters can fit into without affecting the divisions that are already there. If we can do that, then we can solve the problem. So we can divide these up into divisions, and the divisions that we are going to put them in, the half must be able to fit into those divisions, and the quarters must be able to fit into those divisions. So when we put in those divisions, the original division lines must not be affected. That is the way that we can have the fractions to have the same denominator. Why do we say divided in such a way that the divisions are the same? Because the number of equal parts that the whole is divided into will tell us the denominator of the fraction. So if the fractions have the same denominator, it means that they are divided into the same number of equal parts. So we have done that already. One step. Right. So here we have just dividing this one like that. Now we have 1, 2, 3, 4. Do we have 4 equal parts, Jerry?
Yes.
How many equal parts do we have over here?
4 equal parts.
4 equal parts. Because of that, we know that the fractions now may have the same denominator because they are divided into the same number of equal parts. Notice that the first circle is now divided into quarters, but a half of it is still shaded. This one is divided into quarters, 4 equal parts. Do we have quarters here, Jerry?
Yes.
Yes, because it is divided into 4 equal parts. But at the same time, it is half of the circle that is shaded. Is that right?
Yes.
Right. So we have only half of the circle shaded still. The half may now be written as 2 quarters. Do we have half of this circle shaded here still?
Yes.
And know that the half that we have here represent how many of the equal parts out of 4? Right. So we have a half shaded, and it is the same thing as 2 parts out of 4. Therefore, the half that we have here, this half, may be written as 2 parts out of 4 or 2 quarters. Now, Jerry, is it appropriate to write the half as 2 quarters? Is it correct to write this half that we have here, 1 over 2? Is it correct to write it as 2 parts out of 4?
Yes.
Yes, it is correct. So, the like denominators will be the denominator of the answer. So we are going to add them now, since they have the same denominator. So the half is actually 2 parts out of 4. So the fractions have the same denominator and may be added. When we add fractions with the same denominator, the result will have the same denominator as the fractions that we have added. What about the numerator, Jerry? What do we do with the numerators when we are adding fractions?
If they are the same, you add them, but you add them.
Okay, so the numerators, we may just go straight ahead and add them because the denominators are the same. So the numerator of the answer will be the same. The numerator of the answer will be the sum of the numerators. So 2 plus 3, and that is equal to
5.
And that will be the numerator of the sum. So the common denominator will be 4, and the numerator, when we add them, we get 5. So the correct answer is option
C.
We will show that a common denominator means that the whole is divided into subdivisions in which the others fit. So what do we mean by a common denominator? It means that the whole is divided into subdivisions in which the others will fit. For example, if we have a half to be added to 3 quarters, if we have a common denominator of 4, it means that the whole may be divided into 4 equal parts in each case, and each of the shaded portion will be able to fit into the 4 equal parts. In the following number sentence, which name describes 40? 40 is what? Is it the product, the remainder, the factor, or the sum?
Product.
It is the product. Jerry is saying that it is the product. 40. Notice that we are multiplying. If we are multiplying, notice also that the result is 40. The result of multiplication is called the
Product.
option A is therefore correct. So the result of multiplying is the product, and 40 is the result of multiplying 5 and 8. Therefore, 40 is the product of 5 and 8. A is correct. In a product, the first number is the one being multiplied, and it is called the multiplicand. The second number is the one doing the multiplying, and it is called the multiplier. So there we have the multiplicand, and we have the multiplier. The first one is the one that we are multiplying. It is the multiplicand. And the other one is the one that is doing the multiplying, and it is called the multiplier. And the result is called what, Jerry?
Product.
Right, so the result is called the product. When two numbers, say 13 and 2, multiply to give another number, that number, which is 26, is said to be a multiple of both 13 and 2. When two natural numbers, say 13 and 2, multiply to give another number, that number, which is 26, is said to be a multiple of both 13 and 2. And that was discussed at length in videos A. So, 13 multiplied by 2, the result is 26. Therefore, 26 is a multiple of 13 and a multiple of 2. 13 and 2 are factors of 26 because factors and multiples are converses. Although they are multiplicand and multipliers, those are not the only categories in which they fall. So if we say 13 multiplied by 2 is equal to 26. 13 is the multiplicand and 2 is the multiplier. 26 is a multiple of 13 and 2. Also, 26 is the product of 13 and 2. 13 times 2 is equal to 26. It means that 13 is a factor of 26 and 2 is a factor of 26. Which number in the options represents the least common multiple required to add the fractions 1/5 and 3/7? And Jerry is saying that it is 35, which is correct, and that is represented by option A. Why 35? Because when we are adding fractions, we need to take the lowest common multiple of the denominators. So we focus on the denominators and we take the least common multiple of the denominators. The least common multiple needed is the least common multiple of the denominators. That is, the least common multiple of 5 and 7, which is the smallest number that 5 and 7 can divide into without leaving a remainder. And if we are asking for multiples, we may use a term that is related to multiply by saying what is the smallest number that is a multiple of 5 and a multiple of 7. Multiples of a number are the results that we get when we multiply those numbers by the natural numbers. Look at multiples of 5 and 7. That's what we are going to do now. So, multiples of 5 are what we get when we multiply 5 by natural numbers. And we have the natural numbers like 1, 2, 3, 4, 5, and 6. So we have those natural numbers. If we multiply those natural numbers by 5, what we get will be multiples of 5. They will also be multiples of those natural numbers, but we are focusing on the multiples of 5. What are multiples of 7? The result of multiplying 7 by natural numbers. When we multiply 7 by those natural numbers, the results that we get will be multiples of 7. So here we have multiples of 5, and here we have multiples of 7. On the next slide, we will leave out the counting numbers. So we will write down the multiples, but we will not include the counting. We will not include the natural numbers. We will also include a greater number of multiples. Why do we include a greater number of multiples? So that we can catch the common multiple. We will find the least common multiple, which is the smallest number that is both a multiple of 5 and a multiple of 7. And Jerry said that already, even before we started writing down the multiples, that the correct answer is option A, which is 35. We will write down only the multiples of 5 and 7. We will also include a greater number of them than those that we had on the previous slide. So we will write down multiples of 5, 5, 10, 15, 20, 25, 30, 35, 40, and so on. Those numbers that we will get if we will say our 5 times table. 5 1's 5, 5 2's 10, 5 3's 15, 5 4's 20, and so on. And if we say our 7 times table, then we will get multiples of 7. 7 1's 7, 7 2's 14, 7 3's 21, 7 4's 28, and so on. So we have right there multiples of 5 and multiples of 7. The least common multiple is the smallest number that is present in both sets. Least common multiple. 3 very important words. Common means that it is present in all. Well, we only have 2 numbers on this occasion, so we only have 2 lists on this occasion. Common means that it is present in both, or present in all, or an attribute of all. Multiple means that both numbers must be able to divide into that number without leaving a remainder. And least means that we need to find the smallest such number. Multiple, a number that the number can divide into. Common, it is present in both lists. Least, it is the smallest number in both lists. So if we look at the lists, what is the smallest number that is a multiple of 5 and 7?
35.
And Jerry is saying again that it is 35. 35 is the smallest number that is both a multiple of 5 and a multiple of 7. The correct answer is therefore option A, as Jerry said before. The least common multiple means the smallest number that is common to the sets of multiples of the numbers. So the least common multiple means the smallest number that is common to the sets of multiples of the numbers. On the next slide, we will use the table in finding the LCM of the numbers. So let us go straight ahead. We may take another approach in which we use repeated division in a table to obtain our answer. There we have the table. It is our intention to divide those numbers that we have there until the list is exhausted. That is, until the result in each column is equal to 1. In so doing, we will begin with the smallest prime number. And Jerry What is the smallest prime number?
2.
Right, the smallest prime number is 2. Can 2 divide into 5 without leaving a remainder?
No.
7 without leaving a remainder?
No.
We therefore move on to the next prime number, which is
3.
3. Can 3 divide into 5 without leaving a remainder?
No.
Can 3 divide into 7 without leaving a remainder?
No.
Right. We therefore move on to the next prime number, which is
5.
can 5 divide into 5 without leaving a remainder?
Yes.
Can it divide into 7 without leaving a remainder?
No.
Okay. But because it can divide into 5 without leaving a remainder, we will use the 5. Begin with the smallest prime number that is a factor of either 5 or 7. 2 will not work and 3 will not work. So we begin at 5. And we say what? 5 into 5 goes
1 time.
1 time. 5 does not divide into 7 evenly. That means 7 is not divisible by 5. Because 7 is not divisible by 5, we will return the 7 as it is. Now, right here, can 5 go into this one?
No.
But we do not necessarily ask that question, because as long as a column is reduced to 1, then it has no more significance, or we do not give it any more serious consideration. So what do we say? Move on to 7. But we know that this one has already been exhausted, so what do? We carry the 1 down. So the 5 column is exhausted, so we use 7. 1 will return in the 5 column. And then we say 7 into 7 gives
1 time.
So there we go. And what that means is that since 1 is in the 5 column and the 1 is in the 7 column, it means that both columns have been exhausted and we do not need to go any further. The columns are all reduced to 1. We may write down the LCM of the numbers. The LCM of 5 and 7 is the product of those prime factors. So the LCM 5 times 7 is equal to
35.
As Jerry stated at the beginning of the solution of this problem. When numbers do not have a common prime factor, I call them exclusive numbers, and their LCM is their product. So if we have two numbers of which we are required to find the LCM, if they do not have any common prime factor, then the LCM will surely be the product of those two numbers. Now we will investigate the need for a common denominator and why a common denominator works. Why do we need a common denominator? Why does a common denominator work? So we have two fractions. The first one is
half,
and the second one is
2/3.
right. So this one is 1 part out of 2 and this one is
2 parts out of 3.
2 parts out of 3. The red represent 1 part out of 2 equal parts. That's a half. And the blue represents 2 parts out of 3 equal parts, which is 2/3. So there we have 1 part out of 2 equal parts. 2 parts out of 3 equal parts. we need to add the fractions, but they do not have the same denominator. Can we add them immediately?
No.
We cannot add them immediately. And the denominators do not have a common prime factor. So the denominators do not have a common prime factor. And when the denominators do not have a common prime factor, what does that mean?
You have to find a denominator for both sides.
Right. We will find a common denominator. But because they do not have a common prime factor, then the common denominator will be the product of the two of them. And students may do well to remember this, and it will be applicable and very useful throughout your entire lifetime in mathematics, that when the two denominators do not have a common prime factor, the lowest common multiple will be the product of the two of them. So 2 3s.
6.
Right. So the common denominator will therefore be the product of the two denominators. 2 3s. 6. So the common denominator will be equal to 6. The common denominator is 6, means that the wholes may be divided into 6 equal parts. Is that right, Jerry?
Yes.
Right. So if we find the common denominator and we have found it to be 6, 6 is the common denominator. This whole is divided into how many equal parts, Jerry?
2.
And this whole is divided into how many equal parts?
3.
Right. But we are saying that without affecting the arrangement that we have here, it is possible to divide each whole into how many equal parts?
6.
And that we have to do in order to add the fractions. So we will do that on the present slide. Notice that the first is still divided into 2 equal parts, and the second is still divided into 3 equal parts. Just as the diagrams are, divide them into 6 equal parts. So we need to divide them into 6 equal parts. Can we divide them into 6 equal parts?
Yes.
We can surely divide them into 6 equal parts. Why? Because 6 is the common denominator. And a denominator of 6 means that the whole is divided into 6.
Equal parts.
Right. 6 equal parts. Notice that we are not affecting the arrangement that we have there. We are keeping the red part still, and we are keeping the blue part still. How many equal parts is each one divided into?
6 equal parts.
Right. So step back and we will realize that dividing each diagram into 6 equal parts does not affect the original divisions into halves and thirds. So notice, step back, it is divided into, this one is divided into how many equal parts right here?
2.
And this one is divided into how many equal parts?
3.
3. Right. So we are dividing them now into how many equal parts?
6.
Into 6 equal parts. And by dividing them into 6 equal parts, the original division is not affected. And it should not be affected because 6 is a common multiple of 2 and 3. The common denominator is 6. Therefore, halves may be divided into sixths, and thirds may be divided into sixths also. So there we have the 6 equal parts of each of those diagrams. Notice that a half now represents 3 parts out of 6. Can you see that, Jerry?
Yes.
The half that we had there is now how many parts out of 6?
3.
3 parts. And 2/3 now represent how many parts out of 6?
4.
Right. The 2/3 now represents 1, 2, 3, 4 parts out of 6. Each third is 2 parts out of 6. So 1/3 is 2/6. And a half is
3.
right. So a half is 3/6. So the half is 3/6 and the 2/3 represent 4/6. So we may rewrite those fractions in sixths. Because halves can be divided into sixths and thirds can be divided into sixths. When we are adding halves and thirds, we may use 6 as our common denominator, right? Because halves can be divided into sixths and thirds can be divided into sixths. We want to add the 2 fractions that we have there. The denominators are not the same and both of them are divisible by 2 and 4. The common denominator is therefore not the product of the 2 numbers. Why is it that the common denominator, which is the lowest common multiple of 4 and 8, is not the product of 8 and 4? Why? Because the 2 denominators have common prime factors. As a matter of fact, they have a common factor that is not a prime number. The common denominator is therefore not the product of the 2 numbers. Some of us may see straight away that the common denominator is 8. However, we will show by making use of the table how we may arrive at 8 as our common denominator. The common denominator is 8 on this occasion. And, of course, 8 is not equal to 4 times 8. 4 8s?
32.
Right, Jerry is saying very quickly that 4 8s, 32. But we are not using 32 as our common denominator because there is a number smaller than 32 that 4 and 8 can divide into without leaving a remainder. And this is so because 4 and 8 have common factors. We have already decided that 2 will be our first prime to divide by. Remember that when we are operating the table, we begin with the smallest possible prime number. What is the smallest possible prime number?
2.
So we will use 2. Can 2 go into 4?
Yes.
2 times. Can 2 go into 8?
Yes. 4 times.
So 2 into 8 goes 4. Can we use 2 again?
Yes.
You're right. So 2 can go into 2 how many times?
1.
And 2 into 4 goes?
2.
No. Can 2 be used again?
No.
Can 2 be used again?
Yes.
Yes, 2 may be used again because we have a 2 in one of the columns. Although the other one has been exhausted, we have this column that has not been exhausted, and 2 is a factor that can go into this one. 2 into 2 goes one time. We still see a multiple of 2 in one of the columns. So 2 may be used again. May 2 be used again?
Yes.
Yes. And what do we do with this column?
Carry down the 1.
We will just return the 1 because that column has already been exhausted. And then we say what? 2 divided by 2 is equal to 1. So right there and then we have the 2 columns being exhausted and the table has been exhausted. So the LCM of 4 and 8 is the product of those prime factors. What is the product of those prime factors? 2 times 2 times 2, and that is equal to 8. The LCM of 4 and 8 is 8, which is one of the 2 numbers. This will always be the case when one of the 2 numbers is a multiple of the other. Since 4 can divide into 8 without a remainder, we are sure that 8 is a multiple of 4. So, when we have 2 numbers, to find the LCM of those 2 numbers, if one is a multiple of the other, then the LCM will be equal to the larger number. And if the 2 numbers do not have a common prime factor, then the LCM will be the multiple of those 2 numbers. So we have 5/8 and 3/4, and we intend to add them. There are the shapes. One is divided into 4 equal parts, and the other one is divided into 8 equal parts. So this one is divided into 4 equal parts called quarters, and the other is divided into 8 equal parts called eighths. That one is divided into 8 equal parts, and the other is divided into just 4 equal parts. The fractions are in reference to 3 parts out of 4 equal parts and 5 parts out of 8 equal parts. So the 2 fractions, the one for quarters, 3 parts out of 4, and the other for eighths, 5 parts out of 8. So let us adjust our game to reflect the fractions that we have there. One is 3 parts out of 4, and the other is 5 parts out of 8. There we have 3/4 and 5/8. The common denominator is 8, as we determined on the previous slide. Each object should be divided into 8 equal parts. Why is it that both objects should be divided into 8 equal parts? Because 8 is the common denominator. 8 is the LCM of the 2 denominators. Therefore, in adding the fractions, each one of those objects must be divided into 8 equal parts. We have no difficulty with the second one, which is already divided into 8 equal parts. However, the first one needs some amount of adjustment by dividing it into 8 equal parts. At the same time, dividing the object, the first one, into 8 equal parts should no way interfere with the divisions that we have there already. One is already in 8 equal parts. Let us divide the other. So the divisions that we are placing in the first diagram must not affect the divisions that are there already. If the divisions that are there already are affected, it means that 8 is not a common divisor or a common denominator. The 3/4 now represent how many parts out of 8?
6.
1, 2, 3, 4, 5, 6. Notice that what we have here is 1, 2, 3/4. Then we divide. When we divide, we get 1, 2, 3, 4, 5, 6, 7, 8 equal parts. So there we have 8 equal parts. But how many of those equal parts are shaded?
6.
6 of those equal parts are shaded. 6 parts out of 8 are shaded. Because the 6 parts out of 8 are shaded, then we have 6/8. So the 3/4 that we have there may be represented as 6/8. 6 of those parts out of 8 are shaded, meaning that 3/4 are exactly the same as 6/8. The fractions now have the same denominator and now may be added. By looking at the red part, we may see that 1/4 represents 2 parts out of 8. So just looking at the red part that we have here, remember that the red part all by itself represented 1/4. It represented 1 part out of 4. However, when we divide the object into 8 equal parts, that quarter turns out to be 2 parts out of 8. So 1/4 is therefore 2/8. Quarters may be divided into eighths. What helps to simplify this problem is that the options are all having the same denominator. So the options have the same denominator. Which fraction is the same as 5/6? What fraction is the same as 5/6? That is our problem. We need to identify among the options the fraction that is the same as 5/6. What helps to simplify this problem is that the options all have the same denominator. Notice that the options all have the same denominator. Since one has to be correct, it means that the denominator of 5/6 must be transferable to 30. All of them, the denominators are equal to 30. Therefore, since one of them must be correct, it means that the denominator of 6 must be transferable to 30. So let us write that down. 5/6. The 6 must be transferable to 30 because one of these options must be right. We need to transfer 6 to 30. What number do we use to multiply 6 in order that the result is 30?
5.
Jerry is saying that it is 5. which is correct. That is the same as saying 30 divided by 6. We should know it straight away because of our multiplication table. So, there is our multiplication table, and we need to transfer this to 30. So 6 5s, 30. So we need to multiply this 6 by 5. The number that we will multiply by is 5. But we cannot do it to the denominator alone. That will change the value of the fraction. We need to do it to the numerator also. So if we change the denominator by multiplying by 5 in order to get 30, we need to do it to the numerator also, because if we do not do the same to the numerator, then the value of the fraction will be changed. So we multiply both numerator and denominator by 5. And what will be the result? 5 5s, 25, and 6 5s, 30. So our answer will be option D, which is 25 out of 30, or 25 over 30. The correct answer is option D. One alternative that is not so quick is to reduce each of the fractions to their lowest terms. Option A may be reduced by a common factor of 5. So if we reduce this by a common factor of 5, we get 5 into 5 is equal to 1, and 5 into 30 is equal to 6. Our answer will therefore be 1/6, which is not correct. Option B may be reduced by a common factor of 6. So 6 into 6 is 1, and 6 into 30 is 5. So the result will be 1/5. The numerator and denominator of option C do not have a common factor. It may not be reduced. Therefore, option C may not be reduced because the fraction that we have there, the numerator and the denominator, does not have a common factor with the exception of 1. So we may say that it does not have a common prime factor. It may not be reduced. We already know that option D is correct. All that we need to do is reduce it by a common factor of 5 to prove our point. So we have option D right there. Reduce that by a common factor of 5. 5 into 25 is 5, and 5 into 30 is 6. So what do we have? 5 6. Which is, what fraction is the same as 5/6? The one that we reduced to give 5/6 is option D, and option D is therefore correct. Multiplying the numerator and denominator of a fraction by the same number does not change its value, only its form. Also, dividing the numerator and denominator of a fraction by the same number does not change its value, only its form. How do we write the fraction 3/4 as a decimal? How do we write the fraction 3/4 as a decimal? What we are doing on this occasion is proving that when we multiply both numerator and denominator of the same fraction by the same number, it does not change the value of the fraction. So let's go straight ahead and do it. Multiply both numerator and denominator by the same number. As a matter of fact, we will not do that immediately. What we will do is write 3/4 as a decimal fraction. So 3/4 means 3 parts out of 4. Arithmetically, it also means 3 divided by 4. So what do? We say 4 into 3. We can't. At least we can't a whole number of times. So we cannot do that a whole number of times. So we place what there? A 0. And a point. Place a 0 after the 3. So we first say 4 into 3, we can't. Over 3, place a 0 followed by a point. Then we place a 0 after the 3. And what do we say? We say 4 into 30 goes 7 times. And we need to be mindful of our multiplication table. 4 into 30 goes 7 times. Is it that 4 times 7 is equal to 30?
No.
4 times 7 is not equal to 30. But the whole number part is 7, or we may say the quotient is 7, and there will be a remainder. So we say 4 sevens.
28.
Right, so we need to make use of the product of 4 and 7, which is 28. And what do we do with that 28? We subtract it from 30. And 30 minus 28 will give us what?
2.
So 30 minus 28 will give us 2. What do we do next?
Add a 0.
Right. 4 into 2, we can't. Place a 0 after the 2. And we then say what? 4 into 20 goes
5 times.
5 times. 5 fours.
20.
That is what we say next. 5 fours, 20. And we subtract 20 from 20. And the result is?
0.
Right. So because the division gives a result of 0, finally, then we are sure that the division has come to an end. Because no matter how many zeros we place here, the result will still be 0. And if we divide 4 into 0, the result is 0. So, by getting 0 right here, we are sure that our division has come to an end. And what we were dividing to determine? To determine what 3/4 is in decimal fraction form. So 3/4 turns out to be 0.75. And this is a result that students should bear in mind so that you do not forget this for your entire lives. That 3/4 is 0.75. And we are showing that if we multiply a fraction by a whole number, it does not change the value of the fraction, but it changes the form. So if we multiply both numerator and denominator of the same fraction by the same number, it changes the form of the fraction, but it does not change the value. So the value of that fraction that we have there, which is 3/4, that value is 0.75. Now, let us take that same fraction, which is 3/4, and multiply both numerator and denominator by 25. 25 times 3 is equal to 75, and 25 by 4 is equal to 100. And Jerry said that the result is 75 over 100. On the next slide, we will divide 75 by 100. This will be done by reducing 75 by 2 places of decimal. So remember that 3 over 4, which is 3/4, is actually 0.75. We have the decimal representation of 3/4, which is 0.75. And also, when we multiplied both numerator and denominator of 3/4 by 25, we get 75 over 100. When we multiply the denominator and the numerator of a fraction by the same number, its value does not change, only its form. We will show that 3/4 and 75 over 100 are the same. So let us write 75 over 100 as a decimal fraction by reducing 75 by 2 places of decimal. So we have 75 over 100, which is what we have right here, and we are going to write that in decimal form by reducing by 2 places of decimal. In a whole number, the decimal point is located at the right. 75 is that whole number. The decimal point is located at the right. Let us now reduce 75 by 2 places of decimal. Why 2 places of decimal? Because we know that this power of 10 that we have here is 2 because of the 2 zeros. So because of these 2 zeros, we know that the power of 10 is 2. So we will reduce the 75 by 2 places of decimal. 1, 2. We may place a 0 to the left of the point. So 3/4 is equal to 0.75, and 75 over 100 is 0.75. How did we arrive at 75 over 100? We took 3/4 and multiplied both numerator and denominator by 25. So multiplying by 25 both numerator and denominator resulted in 75 over 100. But we see that by doing so, the value of the fraction did not change because both of them are still equal to 0.75. The two fractions give the same decimal fraction. They are equal. Multiplying the denominator and the numerator of a fraction by the same number does not change its value.